Hello everyone. Today we are going to talk about gradients and Hessians of functions and finding how functions can change in a certain direction by looking at their derivatives. So recall that we are trying to minimize an unconstrained nonlinear function. And the nature of our algorithms is iterative. We are moving from point x1 to x2 to x3 and so on and so forth, and we would like to converge to a desirable point, which is a locally minimum. At every point x1, x2, x3 that we visit, the only information that we have is the what we call local information, which is the value of f at the point I'm currently at, its first order derivative, which is the gradient at that point, and then the second order derivative or the Hessian at the current point. Using this local information, I need to find a good direction and the distance to move in that direction. So that is the nature of the algorithms that we will be discussing henceforth. So if my current point is x1, then the new point would be x1 plus alpha times s, where alpha is the step length, which is a scalar, and s is the direction. So this would be my new point, and similarly to go from x2 to x3, I will need another step length and another direction to move. These x's are vectors, so really this equation is of this form. Component wise, if I want to write it, and this would be useful in our discussion today. Alpha is a scalar. It tells us how far we want to move in the direction s. So just to repeat, I am currently at x1. I know this point. I know the derivatives at this point. I don't know alpha. I don't know s. I want to choose them in such a manner so that my function gets reduced, the function value gets reduced, and I converge towards a desirable point, which is a locally minimal point. So how am I going to estimate alpha and s? So this can be found out using derivatives. Which really estimate how the function changes as I move slightly in the neighborhood of the current point. So let's talk about the first order derivative. So let's again say that my new point x is my old point plus alpha times s. Then what is my fx in terms of f of x1 plus what? Okay, so this is the part that I want to estimate. If I don't have any local information, I can just say that fx is nearly going to be equal to fx1. That, if that is the only information I have. But now, since I have derivatives, I can do better and say that the new value is not going to be exactly same as fx1, but I can estimate how different it is going to be based on the derivatives. So let's look at the first order derivative first. So let's see what could be del of fx by del of alpha. So I'm trying to measure how the function changes as I go farther and farther in a given direction. So here I'm trying to evaluate the rate of change of f once I know what s is. So just for clarity, let's write it like this, with a slight abuse of notation. And this is what is this going to be? So remember that f is a function of several variables. It's not a function of one variable. It is a function of n variables. And alpha is a scalar. So I need to apply chain rule of differentiation, which just says that break this differentiation into the individual components on which f depends upon. So this is really going to be d by d alpha of the first component as a function of alpha. Remember that x is a function of alpha and s is fixed, times the gradient of f at with respect to the first component, and we have to add similar n terms, one for each component. With respect to x2 and so on and so forth, I will have n terms in all. This is our chain rule in action in multiple dimensions. So this can be simplified further. So this term, since x1 is so the first component of x is just x11 plus alpha times s1. And if I substitute the value of x1 here and take the derivative with respect to alpha, I'll get s1. and rest is as it is. And in a vector notation, I can just simply write it as S transpose gradient of F. Because remember from previous lecture that the gradient of F is precisely a vector of partial derivatives, these terms, second terms in each of these terms. And S is your vector of S1, S2, so on. This is also same as gradient of F transpose S, and this is really a scalar. Because we are measuring the rate of change of F with respect to alpha, which is a scalar, and F is scalar valued, so this has to be a scalar. Another way of looking at it is we just look at how F is changing in each direction. So how does F change along x1 is given by this term. And if I'm moving a little bit, and this tells me how much I'm moving along x1, so the direction S has an S1 component along x1, so I'm moving S1 distance along x1. So this gives me a rate of change along x1. And similarly, to compute the overall change, I need to sum up all the changes along all directions. So intuitively, this expression makes some sense. So the book calls this term as slope of function f along direction s. We can also look at the second derivative of how the slope of the function changes with alpha. So along the same lines, d square f by d alpha square. So again, I am interested in knowing how f is changing with respect to alpha once s is fixed, the direction is fixed. This is d by d alpha of df by d alpha, and this term is your slope that we computed earlier. So I can rewrite it as d by d alpha of my previous expression, which is this. And using the same line of thought as earlier, this is actually a scalar, so I can bring out the constant. So s is not a function of alpha. I can write it like this, and using the same line of arguments as earlier, this comes out to be S transpose grad square F into S. Okay, so recall that this term is your Hessian which is a square matrix of size n cross n with terms like these. The Hessian is a symmetric matrix, assuming that the function is well behaved. That means twice differentiable. So that means this term is same as this term. Only the order of differentiation changes, and that doesn't lead to any different values. These two values will be same. So this value of double derivative with respect to alpha is called curvature of f along direction s. So what you should try on your own is verify that in one dimension the above formulas make sense. And you see something familiar which is very intuitive when n is 1.